Hey everybody, we're live and in stereo. I just have to discuss two quick concepts with you all, and tomorrow I'm going to discuss one other short concept, and day after tomorrow we're going to have our last class, which is going to be for titration curves, and then I'm going to give you guys 1 week off to just cool off, right? So that's why I'm keeping these classes short concepts, because all of this is pretty simple, it's pretty easy, it's a piece of cake. Everybody has studied acid, bases and salts in their O levels and IGCSEs, and in A levels, we obviously just add it onto our building, but we also discussed all the prior concepts in detail, so that those who have not been taught O level IGCSE in a conceptual manner, they are also at par with us on concepts. And that is the reason why I want to teach these two small concepts to you guys, so that if your O level IGCSE knowledge is not at par, you should join us in our conceptual approach. Okay, what are these two concepts? Well, the first concept that I want to give you guys is the idea of equivalence point. So EQUIVALENCE, equivalence point, right? These are just two short concepts which you should have already been taught in O levels and IGCSE, but I want to clarify it in A levels, right? We don't want to have any confusions in A levels. Okay? So, what is equivalence point? Basically, in an acid-based titration, whenever you perform a titration reaction, and you've already studied it in moles and stoichiometry, we've already done it. But whenever you perform an acid-based titration, we realize that there's something called equivalence point. And what is equivalence point? It is the point at which enough alkali has been added from the burette. Maybe you have alkali in the burette, let's suppose, and you have acid right here, right? So this is my acid, and that's my alkali. Now, equivalence point is the point at which enough alkali has been added from the burette, right here, from the burette, to react with all the acid in the conical flask. That's what equivalence point means. It's a point where enough alkali has been added to neutralize or to react with all the acid in the conical flask. Or you could say it vice versa even. You could even define equivalence point as, when enough acid has been added, from the burette to react with all the alkali in the conical flask. So you could define it either or, it doesn't really matter, but the idea is that enough volume of acid is added to react completely with this alkali which is in the conical flask, or enough alkali is added, enough alkali is added to react with all the acid in the conical flask, and that is when the equivalence point is reached, right? And this is going to help us later on when we talk about titration curves. Now, please understand that if there is a reaction in which you have a 1:1 stoichiometry, for example, you have HCl reacting with NaOH, and this is an acid-base reaction, right? This HCl is my acid, obviously, and NaOH is my base, or alkali. You could call it alkali. Alkalis are just soluble bases, right? Doesn't really matter. So it gives me NaCl, which is the salt, right? Sodium ion reacts with the chloride ion to give you the salt, and hydrogen ion reacts with the OH to give you water, right? So salt and water obviously forms. Obviously studied in chapter number 4 and been studying this from O levels and IGCSE, right? So if there's a reaction in which, and if you were to balance this out, this is just what? 1 mole of acid reacts with 1 mole of alkali. So if there's a reaction in which there's a stoichiometry between acid and alkali of 1:1, this means what? This means that equal number of moles of acid are going to react with equal number of moles of alkali. That's what it means, right? This 1:1 means that if you have 1 mole of HCl, it would require 1 mole of NaOH to completely react with each other, right? So you need to have 1 mole of HCl to react it with 1 mole of NaOH, right? This literally means that you need to have equal moles of acids and alkali. But if you have a stoichiometry which is maybe 2:1, 2:1 or whatever, 3:1, whatever the ratio is, that just means that now if it's 2:1, it means what? It means that the ratio of moles required for the equivalence point is also 2:1, right? So if you were to reach equivalent point, the ratio should also be, let's suppose, for example, I'll give you an example. H2SO4 is my acid and NaOH is my alkali, right? So now if you were to look into this reaction, what's going to happen effectively? This would react together. You're going to get Na2SO4, sodium sulfate plus H2O. Now if you look at the reaction, it's 1:2. Right? This is the reaction. You can balance it out. You can balance it out. This is what you're going to get, 1:2. And obviously, you can balance out the entire equation. This is 2H2O. We've learned balancing in quite a lot of detail in prior classes. So you realize that, hey, now the stoichiometric coefficients are 1:2. So the moles required for the equivalent point should also be 1:2, right? So this is the idea behind equivalence point. It does not, please understand, it does not depend on the volume. The volume can vary. The volume can vary. Equivalence point has to do with the moles. The mole, when is equivalent point reached? When the moles of the acid and the moles of the alkali are stoichiometrically equivalent to each other. Which means that you need to add enough volume of alkali so that it reaches the stoichiometry of 1:1. You need to add enough alkali. Let's suppose here we're adding alkali. You need to add enough alkali so that it reaches the stoichiometry of 2:1. That's the idea behind equivalence point, that you need to add enough alkali from the burette to react with all the acid in the conical flask, or you need to add enough acid from the burette to react with all the alkali in the conical flask. And how do you know it's enough? Well, you know it's enough through your molar coefficients. Stoichiometrically, they are equivalent, right? And this is also known, this equivalence point is also known as the end point. So you could call it equivalence point or you could call it end point. It doesn't really matter. Which is basically what? End point or equivalence point is basically when enough alkali has been added from the burette to react with all the acid or vice versa, right? Great stuff. Now, this end point, when we talk about end point, it's the same as equivalence point, right? But please understand that this end point marks the completion of the reaction. When you reach the end point, the reaction is effectively complete. The moles of acid and base are now stoichiometrically equivalent to each other, and you should stop your titration. And we've done all titration calculations in moles and stoichiometry, so you are well versed with it already, right? Now, this marks the completion of the reaction. And how do we know that an endpoint has been reached? We know because the indicator changes color. And by the way, already studied in acid bases and in moles and stoichiometry. So indicator changes color. Right? And what is an indicator? It's just a chemical substance which gives you a different color in an acid and a different color in a base. Or an indicator is a chemical substance which changes color with the change in pH. That's the same idea, right? So how do we know equivalence point or end point has been reached? Well, the indicator would change color, and you must have performed practicals as well up until now in your A-level chemistry lab, right? But if you haven't, I still have discussed it in quite a lot of detail in moles and stoichiometry, right? Now, at equivalence point, you may contain, salt and water. You're going to have salt and water. But please understand, there's a common misconception from O-levels and IGCSE, which is what? That at equivalence point, students say that the pH of the entire solution now is going to be 7. That's absolutely incorrect. It's not necessarily 7. Because understand that at this particular point, at the equivalence point or at the end point, the solution consists of salt and water, and this salt does not necessarily have to be pH 7. The only salt that is pH 7 with you as of now that you know of is NaCl. That is a pH 7 salt, right? Other than that, it's not necessary that you are going to end up with a pH 7 salt. If you studied this in O-level and IGCSE, that salts are all pH 7, you've studied incorrect information. Not all salts are pH 7. Which salts are pH 7? Sir, you're going to get pH 7 salts usually when you react a strong acid with a strong base. And why does that happen? That's a story for another day. Strong acid with a strong base. That is when you get pH 7 salts normally. For example, when you take HCl, which is a strong acid, and you react it with NaOH, which is a strong base. So you end up with a salt which has a pH of 7, sir. And you get H2O. But normally at equivalence point, the pH is not really 7 at all times, because understand that you can have salts with different pHs. Because if it's a strong acid and a strong base, you're going to normally end up with a pH 7 salt. That's just a fact for now that you need to know, and we're going to learn the whys later on. But and on the contrary, if you have a weak acid or a weak base, if any of the two is weak, if you have maybe HCl reacting with NH3, maybe, a weak base, or you have a weak acid reacting with a strong base. For example, NaOH is a strong base and it reacts with like a weak acid, CH3COOH, which is ethanoic acid. Now the pH is not going to be 7. The question is why? Why? That's a story of another day. Now it's not going to be 7, but why is if you want to ask me the why behind it, I can't. I can just give you guys a visualization as of now, because once you understand titration curves later on, you'll understand the why behind it. But for now, let me just talk about the visualization, and it'll obviously, hopefully, it'll make sense to you. Just logically speaking, I want to explain it. I don't want to give you guys the chemistry behind it. Just logically, let's look at it, right? So normally, this is a table which is going to show you that normally if you have a strong acid and it reacts with a strong base, see, a salt of strong acid and strong base is normally pH 7. Strong acid, strong base, normally pH 7. But if it's a weak acid, for example, if it's a weak acid, weak acids have a pH of around 2.9, strong bases have a pH of around this, weak base has a pH around this, nobody cares, right? But if you look at the salts of it, right? If you have a strong acid and a strong base, the pH is normally 7. If you have a strong acid and a weak base, the pH is normally 5.1. And I'll tell you the reason for it, the logical reason, not the chemistry reason for it. Think of the logical reasoning for it. The logical reasoning is, see, if you have a strong acid, this guy is powerful. Right? I'm just giving you guys logical reasoning as of now. And weak base, this guy is weak, It's pretty feeble. It's weak. So when they form a salt, it's going to be inclined more towards the acidic end. And that's why you'll see that the pH is lower than 7. It lies more towards the acidic end due to the nature of the acid. It's a strong acid. It fully ionizes in an aqueous solution, whereas a base does not fully ionize. So at the end of the day, when you form salt, you're going to still have some H plus ions. And that's going to therefore give you a pH of less than 7, right? And if you have a weak acid and a strong base, now where is the inclination going to be? This guy is stronger. This guy is stronger. So the inclination is going to be towards this base right here. And you'll see the pH is now normally greater than 7. It's about 8.9. And similarly, if you have weak acid and a weak base, that can effectively give you a pH of 7, because now the inclination is nowhere. They're both the same. The inclination is nowhere. They're both the same. But here the inclination is more towards the acid. So the pH is lower. And because lower pH means more acidic. And here the base is stronger. So the inclination is more towards the base and therefore higher pH. Done? That's the idea. That's not the chemistry behind it, but that's just a thought process, right? I'm going to teach you the chemistry behind it in, inshallah, what's it called, in titration curve, although this chemistry you don't need to know, right? So this, Ibrahim, again, you don't need to memorize it. Please, for crying out loud, there's no memorization behind it. These two are the same strength, that's pH 7, the same strength, pH 7, strong acid, weak base. Where's memorization here? This is stronger, the inclination is going to be more towards the acidic, and this is weaker, this is stronger, the inclination is more going to be towards basic. And what's memorizing about it, Ibrahim? Come on. For crying out loud, you don't have to memorize it, and you don't even need to know the why behind it. But for titration curves, these are going to help you. So if you really want to understand titration curves, this is going to help you. And through titration curves, you'll understand the why behind it, which is not part of your course, frankly speaking, right? So that's the idea. And we are effectively done with one short concept. That's it.